Good morning.
Good morning, how are you?
Out of breath. Okay. How are you?
Energized.
Okay.
Looking forward to weekend, which needs a lot of energy.
A little tired.
Did you have a tour?
Yeah, it's been discovered. It's just a lot. It's like a big tour.
It's what?
The biggest tour event of our year.
Oh, okay.
So it's just a lot. But it's fun. And it's nice though.
Yeah.
And my sister was on my tour.
Oh,
It's cool. Great.
where are you from?
The Twin Cities.
Okay. What town? Gotcha.
You
I'm
from
from,
the city?
yeah, I'm from Shakopee.
Oh.
Well, Fire Lake, Shakopee. Graduated from Fire Lake, but live in Shakopee.
Yeah.
The armpit of Shakopee.
The what? The armpit of Shakopee?
Fire Lake. No, I like Fire Lake. We played some kids in soccer there. They're always really nice. Actually, we played in basketball.
They were nice.
Yes. It was a Christian school.
That's cool. From Fire Lake?
Yeah. I don't know. Fire
Was
Lake.
this back in middle school?
High school.
I'm trying really hard to think of a Christian school in Fire Lake.
Pretty sure it was Fire Lake. Maybe I'm mistaken.
Well, there's, oh gosh, St. John's Catholic school. It went through 8th grade.
Let me look it up.
That,
It was very small.
oh gosh, please look it up for me. I don't even know. You're gonna say it and I'm gonna think I'm really dumb. Are you looking it up? Stop looking it up. Look things up.
College.
We're taking a break next week for lab. Let's go. We don't have lab next week?
Not you.
Oh, dang it.
Sorry.
Don't do that to me, Joe.
Oh, we're finishing. I'm finishing my analytical chemistry lab before Thanksgiving.
Yeah.
That's beautiful. I love how we're scheduled like for 2 or 3 days for each lab.
What's the,
No lab is taking more than 1 day.
what's the
The
thing?
finals not.
Our report is due on Wednesday. Still.
School.
After next week. Oh, sweet. I don't have to write that. Okay.
St. Paul's Lutheran. Fire Lake Christian Academy.
What?
St. Michael. That's more of St. Michael.
Oh yeah, it is St. Michael instead of St. John.
Do you have any
Aspen Academy. Is it Aspen?
vision if Morgan will come today?
Sorry, what?
If Morgan will come today?
I have not seen him all day. But
Because Alyssa told that she will not come and Steven typically connects through online, so maybe we do not need to wait for anyone else. Oh, thanks much for bringing
I
it.
have
Fire
heard
Lake.
one.
I think it's Fire Lake Christian Academy.
Where is
So, if the MATLAB homework is too boring for you, you have another one more mathematical. And let's double the credit if you do it by Monday and regular credit if you do it by Wednesday.
Really?
Yeah. Because anyway, everyone does things on weekend rather during the week. You're so busy. And let's create several safety cushions.
Oh my.
Yes, it's my favorite. Very good. Oh, thank you. Ah, no, this effect. So what are we, who we are, what are we doing, what are we going to do? So it's physical chemistry, prediction outcomes of what comes of instruments, experiment, wavy nature of electron, applying to simple objects, right? And maybe the only time when we touched something realistic was the lab last Wednesday, right? So we didn't look at the superpositions and wave functions, we looked only on the energies of electronic states for same chemical composition but different sizes. So what we need to do is to get the same result, same qualitative result, in a mathematical way, right? Again, supposing that we may get transferred to inhabited island without computers, and suddenly we need to predict density of states of two-dimensional, one-dimensional object. So for one-dimensional object, you are fine. You remember that it drops like 1 over x, or 1 over square root of energy. And for the two-dimensional, it should be constant, and for three-dimensional, it should be growing as square root, right? How did we get it last time for one-dimensional object? What was the, who was helping us? Stigma? Looking backwards. So the idea was that we set up, well, you don't set up anything, but you look on two spaces. One space of quantum numbers and another space of energies. And we were walking along, not we, the straw man or whatever, stick man was walking along the space of energies and looking how many quantum states are behind here, right? For one-dimensional space, it was really easy. We just draw a stair and look back. Can we use the same idea for two-dimensional and three-dimensional things? Like, we need two spaces. One space of energies, which through computational modeling in the lab, we definitely see that we do have this space, because it's argument for density of states. And we need a space of quantum states. But space of quantum states will be not one-dimensional anymore, right? Which is a little, I wouldn't say challenge, but discomfort, right? So this stick man would need to look back for a long, for like in many directions. So there is no much intrigue. We will get, I promise, we will get in time the density of states for two-dimensional and three-dimensional. But what's the logic? How would we do it if we never saw this computer simulation? I'm down to cell phone, but it doesn't. How does space of quantum states look for two-dimensional and three-dimensional case? So for one-dimensional, on X, we had energies like 1, 4, 9, 16, 25, and space of quantum states was 1, 2, 3, 4, 5, right? One-dimensional. What will be the set of quantum states if you have two quantum states? For square, it's not box, for square two-dimensional problem, square box in 2 dimensions. There will be two quantum states, n sub x and sub y, right? They both change independently, and they are discrete. So it looks like a chess board with sticks, right? That are like rectangular space with points, right? And then for each point we have certain energy. So we need to look which other combination pairs of this quantum state that give the same energy. Other pairs of quantum states, other limits in the space of quantum states that will give the like area that would correspond to certain energy. Okay, so when we will do it practically, it will be very easy. But it's so much better if we think a little bit forward and imagine what we expect to see. What else do you remember from Wednesday class? So Stickman, I think it was our discovery. Same as Camel for Monday lecture. But what in addition to Stickman was on Wednesday? Number of states, how many steps behind, and then density of states. Derivative of number of states in respect to energy, right? So just based these two concepts, and we are going to apply them. But I see a little inconsistency. We have two concepts: number of states and density of states. And if we have two-dimensional box, then it is not space is two-dimensional. So we need to find number of states in 2 dimensions, right? And if amount of states is infinitely large, then amount of states in some two-dimensional figure would correspond to area, right? You like it? So what are two-dimensional figures that you remember and can find area?
Rectangle.
Super. What's the area of a rectangular?
Base times width.
Super. That's great. What else? Pi r squared. Excellent. So it will be our foundation. So NOS, DOS, and we will add the concept of the area, pi r squared. What if we suddenly become too brave and go from 2 dimensions to 3 dimensions? Huh? Volume, which is huh? Sphere. What's the volume of a sphere?
4/3 pi r to the cube.
Super. So we have all foundations. Now you did the hard work. I do the easy one. I just cook all these ingredients together. It doesn't listen to me.
I don't see any stuff for this hookup.
Looks like standalone computer without internet. Maybe just swap slides.
Oh, you tried to change that.
It doesn't respond to the keyboard. Maybe there is a. Just check if we. Oh, okay. At least it will be listens to the mouse.
Maybe it's detached somewhere.
This is this homework and the stuff here and there for the future, but they will be really easy, especially to differential equations. Number 1 will be super easy, and This one will be very similar to what we did in class, and maybe we didn't. We did it with MATLAB a couple of weeks ago, predicting expectation value. And whence the class will be itself a key to this problem. Okay. So we are still working with those, but if you want to be more formal, we are going from one-dimensional blocks, we are going to like 2- and 3-dimensional blocks. And it is the stuff that you all have submitted, right? So we are looking on how the density of states, number of states per energy interval, depends on the size of the block where electron is allowed to be. And we saw a drop 1 over square root. One-dimensional, it was like flat areas for pizza box, and as soon as it gets to this right, it gets square root. So 1 over square root of energy, constant, and growing.
Yeah, that keep all works.
Super. Thanks so much. If we do have very small size of the box, 0-dimensional, or some people who use the colloquial word quantum dot, then it is discrete levels. And small molecules and atoms, in some sense, also have discrete levels. Right? Also, if you have 3-dimensional, there is no offset between first state, or the offset is vanishing. We do not see it. But if you have 1, 2, and 3-dimensional, the first available state is offset from 0. So there is 0-point energy. And so here offset is 0. Here it is, let's say, some quantity, x. Here is 2x, here is 3x, right? Because here we offset only quantization along 1 degree of freedom, where the rest do not have borders. Here we have quantization along 2 degrees of freedom, and here along all 3, right? So it's adding 0-point energies 3 times. Okay, we were talking about it, and I was thinking about retyping it in a nicer font, but all information is here. So our stickman was working along 1-dimensional, and we got this stuff. And we had eigen functions, only one sign with 1 quantum number, and only 1 n squared over psi squared. But if we want, if we add 2nd dimension, we multiply the function by factor for another dimension. It has independent quantum number. And for energies, we add ny squared, right? So we do need to convert this information into number of states, and then practice derivative of number of states over energy. And you already prompted how to compute volume and area, which will be our background. So it's our friend from last time. And here are our space of quantum states. So we do have states for n x equals 1, 2, 3, and further, right? And for and y we also have 1, 2, 3, 4, but quantum state of this box is defined by a pair of values, right? So each point in this space of quantum states corresponds to one eigenstate of the two-dimensional box. And we already know how to find the energy of quantum state if you have these two numbers, and x and y, right? You have them squared, and if the box has equal sides, we can put size of the box outside of the brackets. So which technical problem I'm trying to solve myself, or which technical problem I need to do. If I follow the pattern, energies, number of states, density of states, I need to convert information about this number of states into number. I have a clear mind, but I do not have a clear verbal formula. We have two concepts: set of quantum numbers and number of states with certain energy. Right? In one dimensions they were coinciding, and here they will be divergent. So we need to count number of states. So how many states have certain energy? So we are going to select specific shape and count number of states inside this shape. Make sense? I just a couple of years ago put it a little better handwriting. So if those are x and y, we know that the larger value of n x and value of n y, the bigger is the energy. And energy is nx squared plus ny squared, right? What is geometric interpretation? Like if something equals x squared plus y squared, what do you remember from? Perfect.
With the radius.
Right. So it's a radius of a circle. And Pythagorean theorem.
Yeah.
So if you have certain value of nx and certain value of ny, it will be this much of radius, right? But radius is for Cartesian space, where we can measure stuff, where we can move physically. But this is abstract space of quantum numbers. So it's not really radius in our common sense, it's radius in a space of quantum numbers, abstract radius. To underline that it is abstract, I put a tilde on top. Okay. So what are your observations? If we select several states that will have the same radius, how similar or different will be their energies? Let's compare state 3, 4 and 4, 3. What will be their energies? Yes. And if we take the state 5, 1, it can be a little off, but approximately the same.
Really?
Yes, everyone that falls into this little ribbon will have the same. Yeah?
Just struck me because it tastes great.
So everything inside a little ribbon will have approximately the same energy, right? What will be the energy of all states below this ribbon with smaller radius. Yes, if you tell that at the edge of ribbon we have some E prime, then for each R smaller than R prime, energy will be smaller than E prime, right? So if we need to count number of states with energies equal or smaller than given threshold, we just count how many points are inside this ribbon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 in this case. But we can set up this edge anywhere else, right? So area under this border will focus us on all states with energy smaller than a threshold. So the stickman should walk from origin away and look back to the origin. And then it will be the same procedure. You will see how many states are behind, in a sense, how many states have the smaller energy. And if the stickman is educated and knows the equation of pi r squared, he can immediately compute with a little correction. Since quantum numbers are always positive, you chop your circle in 4 equal pieces, and it will be pi r squared over 4.
Oh,
Make sense?
it's just in the second quadrant.
Like, I don't know what's the right language. Quadrant?
Yeah.
Right? So in this sense, I would like to focus. I don't know on what to focus. They all make sense. I thought about erasing or retyping, but it's not so bad of calligraphy. So energy is square of x and y, and you put this 0-point energy. And if the sizes of the boxes are the same, we can put 0-point energy outside, and then energy as function of nx and ny will be square of nx squared plus ny squared, right? Which is radius squared, second power of radius in this crazy space of quantum states. So ratio of the energy of quantum state to energy of 0 point ratio of energy of any quantum state to the 0-point energy will be square of this radius in the space. Yes?
Is that just the energy of the ground state in regards to x and y, or what is that?
So E sub E naught is energy of the ground state, and any others are excited states. Since there is only one electron, there is only one ground state. If you promote it from this state 1,1, here, there, or further up, it will be more and more excitations. Later on, we can, well, typically in fundamental part of chemical education, one starts from hydrogen atom, like SPD, principal orbital magnetic quantum numbers, and then use our principle of putting more and more electrons, right? And then they have opposite spins. One can play atom game with this two-dimensional box and put more and more electrons, and they will feel like here, there, similar idea, if we need it. If our atoms will be square rather than spherical. Okay. So this green stuff is good. Now we do need number of states. So we already have this property, and now we need to connect this radius with number of states, which will be pi r squared divided by 4. And r is exactly this stuff. But we do know So it's not much writing and deriving, it's more like staying alert and sober and interpreting what we see. So what's the logic? We can find this radius as function of energy. Originally we go from quantum number to energy. Now we go back from energy to quantum number. Or not literal quantum number, but this radius that characterizes quantum numbers in average. So if you do have energy, we can find this radius. So the radius will be square root of energy of quantum state divided by 0-point energy. And this, so when we need to find number of available states, when we want to practice PR squared equation, we will take this R not from fantasy. We will literally compute it from the energy of states. Energy, then radius, and then number of states. This one is not right because there should be factor in front of it. Oh no, there is no. I'm waiting. There will be good equations for sure. They're all correct, but I feel panicking when there is so many written things. It's better to have nothing and start from scratch. So, number of states will be 1/4 of the PR squared, right? And this radius will be just square root of energy divided by some constant, right? In fact, this constant will be ground state energy, 0-point energy. This one goes into here. Can we plug it in? So basically, we should plug. Oh, wait, do you object this equation? Then this abstract radius is square root of energy of quantum state divided by ground by 0-point energy. No one objects. And no one objects with phi r squared, right? Can we merge them together? Plug in this one into here. And then as a result, we will get number of states as function of energy. And here we apply square of square root, right? Which will be function itself. So number of states will be 1/4 pi, and then energy divided by constant. So number of states with given energy is directly proportional to energy of this state. Number of states with energy smaller than given energy is literally proportional to the value of this energy. It's not my fantasy, it's just what we get by merging these two equations, by plugging this purple into the red. I hope in previous year it was typing it in a better way. Yeah, for certainty, this 0-point energy is formulated as Planck constant pi square mass, size of the box if it is equal sizes, right? And these factors come from like momentum square over 2m, and this is this distance. So if anyone is very picky and meticulous, this energy divided by 0 point energy can be expressed in terms of size of the box and mass. And here is an exercise that any of you would be able to go to the blackboard and complete. But it is so easy that I will do it myself, or just show it. But next time to invite someone, be prepared. So number of, and probably from a side I will crazy because I repeat the same thing like 10 times. So number of states is 1/4 of pi r squared. R depends on energy. And number, then if you do constant times energy, so how many states have energy smaller than a threshold? And then density of states is derivative of number of states over energy. So derivative of constant multiplied by independent variable will be a constant. So whatever the constant appears in front of energy in number of states will be the value of density of states when it comes to this flat regime. So it should be just an inverse of the 0 point energy, right? But, sure. Yeah, there's cancellation of 1/4 to here, and then factor 2 migrates from nominator to denominator. So it's and pi also cancels. So if you plug constant pi here, size, mass. Okay. And if you take derivative, just this e disappears. Density of states equals the larger the box, the bigger density. Yeah, makes sense. The box is bigger, states are denser. Who needs two-dimension? Who needs this pizza boxes? Do you, in your research or regular life, except eating pizza, do you have do you see two-dimensional objects? What are they? What are the examples of two-dimensional objects? Do you write with pens with ink or with pencils with graphite? Huh? Both? Do you know how to receive Nobel Prize in chemistry if we would live 20 years ago? So you take your pencil with graphite, cover like a glass or some glossy surface with equal sides of the graphite. Then apply tape and put this tape with a little bit of layer of graphite into any instrument you have access to. So people who got to this idea got Nobel Prize for it.
You put it in what?
you put this tape with graphite into different instruments like spectrophotometer, NMR, like any instruments. Put in I don't know if they were putting in the EPR, but they were checking applying magnetic field and light simultaneously.
Is it a graphite?
Yes. And if they were cooling it with like liquid helium and checking for properties, but you know that graphite is composed of two-dimensional layers of the honeycomb, and if you tear off this, if you peel it with tape, you basically take one layer of graphite. And then it doesn't interfere with stuff above and below, and the electrons move only in 2 dimensions and are forbidden to move in another one. It shows properties somewhat similar to what we considered right now. Other examples, here this honeycomb. And other materials are molybdenum sulfide, like transition metal, and either disulfide or diselenide. And right now there are, so this one is graphite, molybdenum disulfide in this area. There is a bismuth telluride, which is I'm not focusing on it right now, but seeing that a lot of colleagues are changing direction. And also, this one, it looks like metal organic frameworks, but it is not. There is metal organic framework has 3 dimensions. And here is lead coordinated in octahedral fashion with halides. But it forms periodic lattice in X and Y, and then electrons can move from lead to lead and move freely. But in the Y direction, it is separated by insulating organic layer. And the name for this material, I will be not able to pronounce too long, but you can see it. So like Dan Jacobson phase of lead halide perovskites.
So how, when we say 2-dimensional,
Uh-huh.
is that essentially just how the electron can move?
Yes.
Okay. Otherwise I was really confused. That makes more sense.
Graphite would be considered 2-dimensional.
Graphite is not 2-dimensional, but graphene is. So if you put stacks of a lot of graphene layers, it will be regular graphite that you have in your pencils. If you manage to separate one layer, it will be graphene which has some unique quantum properties. And technique to extract this one layer is very easy. So what are we going to do now in the remaining 9 minutes? What are your expectations? 1, 2, yes. And this is just what you've got, right? Constant. And then because of quantization in other dimensions, you get another constant. And everyone has submitted a movie, and probably by Monday everyone will submit either PowerPoints or MS Word with images like that. So where does the stickman go in 3 dimensions?
Anywhere.
Right, but if we want to use our experience from 1 dimension to 2 dimension, so it should go from 0 to positive values, from origin to larger values, from origin to a surface, and we may also expect that there will be a border that encloses all states with at the border and surface all energies will be the same, and inside they will be less. And this geometrical argument will help to identify number of states with energy less than threshold. And you already helped me to remember the equation for the volume, right? So we should set up critical radius so that in the space of quantum states. So if the box is equal size, then there will be 3 quantum numbers, and x and y and z. One over size of the box squared, and in the brackets we have an x and y and z squared, each of them squared. So it will be radius in 3 dimensions, this abstract radius in 3 dimensions, right? And we see that by fixing value of this radius, we fix the energy. So state over combination of quantum numbers in the sum of their squares will give the same value of the radius, will have the same energy. And if we define radius this way, then we again see a connection between energy and radius. Energy is constant times radius squared. And if you need value of radius as function of energy, like if we inverse direction of our logic, then we need to take square root of energy, right? Square root of energy and then the rest of constants. What else is left to do? Plug in this radius into equation for volume, right? Should we use it plainly, blindly, literally, or should we modify it? Divide by how many?
Oh, 8.
Yes. So in 2 dimensions it was quadrant. In 3 dimensions, octant. Yes. Octant. Same like octahedral, 8 in one of the ancient languages. So here is the John's formula for the volume, and here is 1 over A. So we do have radius as a function of the radius as function of energy is square root of energy times constant, right? So energy times in power 1/2 times constant. So we plug in this radius into this equation. Oh, it was already written here. Energy power 1/2. If we take third power of the power 1/2, what will be the resultant power? Yeah, 3/2. And now, by the following the same pattern, if the number of states with energy equals more than this E tilde will be constant times E tilde to the power 3/2, right? You agree? It's the same logic. Now, by definition, density of states is derivative of number of states in respect to energy. It's too easy. I don't want to disturb you. I'll disturb you with something more complicated. What will be the derivative of independent variable in power 3/2? So 3/2 minus 1.
3/2 either.
Which will be how many?
3/2 either one.
1/2. Right? Which is square root. And it is what you saw in the lab. So for 3-dimensional object, density of states grows as square root of energy. Right?
So is the C tilde encompassing the 1/6 pi C cube, basically?
Yes, yes, and also it encloses size of the box, Planck constant, mass, all the stuff.
Which comes from the original C.
Yeah.
Got
So if you have curiosity, it's optional. And if you carefully, if you take derivative, then it is what you've got in on the simulation. So from now on, you can look on experimental measurements of density of states if they are available, like from scanning time and micro. We were talking about you were planning to teach me a right word for analytical, just electrochemistry experiment, right?
Oh.
So in electrochemistry, one can find density of states, but it will be possible only for few states at the very beginning. You will not get to broad abundance, and typically it is applied to molecules which have just a couple of states explicitly seen. But scanning tandem microscopy can go over very dense states. Absorption spectra, they show transition from those of occupied to those of unoccupied, and it inherits and carries information. So absorption spectra are not equal to density of states, but they are carrying part of this information. And we are not covering it right now, but either looking on measured density of states or measured absorption spectrum, one can guess and identify what is which object is generated. And if the chemical composition is the same, but it is a nanostructures of different sizes and shape, this information encodes shape of the density of states and the absorption spectrum.
So will density of states be directly horizontal absorbance?
No. It will, for absorbance, it will be like square of density of states, and
So
multiplied by.
density is increasing.
Right, and it's also multiplied by oscillator strengths, which is often non homogeneous. So it parses one of the specific states from those that are available. Those peaks are called Van Hoff singularities. I don't know the name of the history of the person who designed it, but it's probably there is one. I don't know if it will play, maybe not, but you saw it, right? And in the lab, instead of doing this mathematical analytical exercises, we just literally practice delta function. Have a nice weekend. Thank you for investing your time into the course. I will be happy to answer emails if you decide to get extra credit for the analytical problem.